At this point, we are entering the second part, namely time-independent perturbation theory. In the previous introductory slides, we already discussed the basic physical idea. When a system is only slightly different from another system whose solutions we already know, we try to use the known problem as a starting point and treat the extra part as a small correction or perturbation. Now we are going to make that statement mathematically precise. So from here onward, the main question is this. Suppose the exact Hamiltonian is only a small modification of a solvable Hamiltonian. How do we systematically calculate the corrected energy levels and corrected eigenstates? That is exactly what time-independent perturbation theory does. Please notice that there are really two distinct outputs in this method. One is the correction to the energy eigenvalue, and the other is the correction to the eigenfunction or state vector itself. In many elementary examples, students focus only on the energy correction, but the wave function correction is equally important because it tells us how the state is deformed by the perturbation and how different unperturbed states become mixed. So the next few slides build the general formalism. We will introduce a perturbation parameter, expand both the energy and wave function in powers of that parameter, substitute the expansions into the Schrödinger equation, and then compare terms order by order. This order by order comparison is the essential mechanism of perturbation theory. Once that formal structure is established, we can later apply it to concrete systems such as a potential well in an external field, the Stark effect, or other weakly perturbed quantum systems. So please view the next few slides as the mathematical foundation. Once the framework is clear, the later applications become much easier to understand. Now let's write the perturbed Hamiltonian in a form that is extremely useful for systematic expansion. We assume that the Hamiltonian of the perturbed system can be written as shown in this equation, where h hat naught is the unperturbed Hamiltonian, h hat prime is the perturbing Hamiltonian, and lambda is called the perturbation parameter. It is easily seen that lambda turns the perturbation on or off. When lambda equals 0, the perturbation is off. When lambda equals 1, the perturbation is on. But the full problem should remain close to the unperturbed one. Also, we can imagine that as lambda varies smoothly from 0 to 1, it takes the system smoothly from the unperturbed one described by the unperturbed Hamiltonian to the fully interacting system described by the full perturbed Hamiltonian. Later we will see that the introduction of the perturbation parameter lambda is just for mathematical convenience. It allows us to keep track of the order of each correction term. In the actual physical problem, we usually set lambda equals 1 at the end. So it will not be part of our solutions to the perturbed system. The stationary Schrödinger equation for the nth state of a perturbed system is then written as shown here. Now comes the central assumption of perturbation theory. Both the exact energy E sub n and the exact eigenfunction psi sub n can be expanded as a power series in lambda. So rewrite the two equations shown here. Let's interpret these terms carefully. The zeroth order energy, En naught, is just the unperturbed energy of the nth state. The first order term, En1, is the leading correction caused by the perturbation. The second order term, En2, is the next correction, and so on. Likewise, psi n naught is the unperturbed eigenfunction. Psi n1 is the first order correction term to the state, and psi n2 is the second order correction term. So conceptually, perturbation theory says the exact solution is not replaced by something unrelated. It is built as a deformation of the unperturbed solution. This point is very important physically. We are assuming that the perturbed state evolves continuously from the non-unperturbed state as the perturbation is turned on. That is why this expansion method is sensible. Also notice that in this formalism, the correction to the wave function is just as systematic as the correction to the energy. So on this slide, the main takeaway is the perturbation parameter lambda is introduced as a mathematical tool, and the exact energy and eigenstate are represented as power series around the unperturbed solution. Since we have expressed both the energy and the eigenfunction of the nth state in terms of lambda, it is clear that the following two limiting cases must hold. This means that when the perturbation is turned off as lambda approaches 0, the exact solution of the perturbed problem must reduce to the unperturbed solution. That is exactly what we expect physically, and it is a good consistency check. Now we carry out the key algebraic step. We substitute the power series expansion of E sub n and psi sub n into the Schrödinger equation. We obtain the equation shown here. Equating the coefficients for lambda to the 0th power, lambda, lambda squared, and lambda cubed, and so on both sides of the above equation, else the last equation shown on this page. We see that the coefficient of lambda to the 0th power contains only the unperturbed terms. The coefficient of lambda involves the first order correction terms and the perturbing Hamiltonian in addition to the unperturbed solutions. The coefficient for lambda squared, as shown here, involves the second order terms, the perturbing Hamiltonian acting on the first order correction term to the wave function, in addition to the unperturbed and first order terms. This is the heart of the method. The reason this works is that if the equation must hold for arbitrary lambda, then the coefficient of each power of lambda must vanish separately. So the single Schrödinger equation for the full perturbed system shown here is converted into a sequence of equations, one for each order in lambda. Now we have the long expanded expression reorganized by collecting terms of equal powers of lambda, as shown in this equation. As described on the previous slide, the sum is 0 only if each summand corresponding to each power of lambda is 0. That is what allows us to write separate equations order by order. So first, the 0th order equation is shown here. This is exactly the unperturbed Schrödinger equation. So 0th order simply reproduces the problem we already know how to solve. Next, the first order equation is given by this equation. It is the first place where the perturbation enters explicitly. Notice that the first order correction to the wave function and the first order correction to the energy are determined by the action of the perturbation operator on the unperturbed state. It is the first order perturbation theory to find solutions for the first order energy correction En1 and the first order correction to the wave function psi n1. Then the second order equation is shown here. This has a similar structure, but now it involves the first order corrected state and the second order energy correction. The second order energy correction and the second order corrected state, En2 and psi n2, will be determined by the second order perturbation theory. So we clearly see the recursive pattern. Each higher order equation depends on the lower order quantities. Please notice that the unperturbed Hamiltonian operator, the perturbing Hamiltonian operator, and the first order correction terms to the wave function and the energy are all known quantities. This statement is crucial. Perturbation theory is possible only because we start from a fully solved and perturbed problem and a specified perturbing Hamiltonian. Also note that psi n1 and psi n2 right here are generally not independent eigenstates. They are correction terms to the nth state. So the perturbation problem has now been converted into a sequence of equations. We have zeroth order equation, first order equation, and second order equation as shown. Now at this stage, you may ask, do we solve these equations directly in differential equation form? In principle, you could try, but in practice, the standard and much more elegant procedure is to project these equations onto the basis of unperturbed eigenstates. That's how we derive explicit formulas for the first and second order energy correction terms and the expansion coefficients of the perturbed state.